残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Okay, what's up guys? We're back today with a little bit of bonus math. So today we're going to talk a little bit about differential equations. So this is not the focus of our class. This is not what Calc 1's about. But differential equations, we've got enough stuff now to really be able to deal with some of the fundamentals and the basic types of things you might encounter. Or at least we have enough to introduce the topic. Differential equations is a very large field. It is substantially larger than what we will get into today, but now that we know the basics about integration, or at least indefinite integrals, we have enough to introduce at least the concept of a differential equation. So it's not the focus, like I said, this is just some bonus math. This is not our focus, but it certainly is a powerful and undeniably valuable tool. Knowing about differential equations is a really good thing. It is a very, very useful skill. So, an equation involving an unknown function and its derivatives is what constitutes a differential equation. So, we have an equation, it has some function, which we don't know, that's what we have to find, and the equation involves the derivatives of that function. That's what makes up a differential equation. So let's try probably the most basic type of differential equation that I can think of to get started, just to get familiar with the concept. So let's just suppose we know that the derivative of a function f satisfies the equation f prime of x is 2x plus 10. So if we want to solve this differential equation, we would notice that a function f that satisfies this thing right here is a function which is an antiderivative of 2x plus 10. That is, the functions that satisfy this, all of the solutions, they're antiderivatives. Okay, so as we know, we can take an antiderivative by doing an indefinite integral. So we take the indefinite integral of 2x plus 10 dx, and just through a quick application of the power rule, we get x squared plus 10x plus c, where c is some constant, could be whatever you want. So these are all of the different solutions. C is an arbitrary constant, you can pick any one and it'll still work. And this gives us an infinite number of solutions. And every single one is of the form f of x is x squared plus 10x plus c. So this is pretty much exactly what we've been doing. This is really all there kind of is in this section is a way to undo a differential, or to solve a differential equation, to undo a derivative. Now, there are a lot more complicated differential equations than this. It gets a whole lot more in-depth and a whole lot more interesting if you go more into differential equations, but this is enough to get us started. Normally, though, you'll have a little bit more data, so let's talk about that. Now, stepping back a little bit, we could consider a more general type of differential equation. One of the form perhaps something like f prime of x is g of x, some function of x. So, and another way you could see this, just to maybe get this a little bit more familiar if you've seen some differential equations before, or just to familiarize you for when you do see them eventually, if we write, as we often do, something like y equals f of x, then this guy right here just says that y prime is equal to g of x. So we're given this, and we have to find f. That is, we have to find out what y is. This is analogous to how we wrote things when we were talking about implicit differentiation. So if we do things this way, we really can start to see a little bit better what's going on. So here we've got a known function g, this is given to us, and f is unknown. That's what we got to find. That's the solution of the problem. Naturally, since f prime of x is g, this means that f of x is an antiderivative of g. So this means that we'll find out what f is just by finding an antiderivative of g, which just involves taking an indefinite integral of g. Now, this part is only sort of true. Sort of. Perhaps the more accurate way to say this is that f of x is in the set of antiderivatives of g of x. There are an infinite number of them. Up to an arbitrary constant, it is this, but that choice of arbitrary constant, each different choice specifies a different function. That's to say something like x squared and x squared plus 1, they're not the same function. So this involves an arbitrary constant. In practical cases, a differential equation is very frequently accompanied by what's called an initial condition. This will allow us to determine which constant we should choose. That is, we have two pieces of data. We have f prime of x is g of x, where g is given, and then we have f of a is equal to b, where a and b are given. So we have info about the derivative, and info about the function. So info about the derivative is enough to specify the function up to a constant. When we get information about the value of the function at a point, we have enough now to specify what that constant is. And this type of a problem is called an initial value problem, or frequently shortened to IVP. Okay, so IVPs are differential equations with one extra piece of data, and all that is the value of the function at one point. Let's try one out and see if we can do our first initial value problem. Okay, so let's try out our first initial value problem. Let's solve a differential equation and then use a little bit of extra data to figure out which one of the infinite number of solutions is the one we really need. So let's try it out. Let's solve the initial value problem f prime of x is equal to x squared minus 2x with the extra piece of data. This is what makes it an initial value problem. F of 1 is 1/3. So two pieces of data, these two things together specify the initial value problem we're going to solve. So the first thing we'll notice is that our solution f has to be an antiderivative of x squared minus 2x. Just by definition, since the derivative of f has to be x squared minus 2x, f has to be an antiderivative of that quantity. So just doing a quick indefinite integral, just noticing that the indefinite integral of x squared minus 2x dx is just by the power rule, given by 1/3 x to the third minus x squared plus a constant. this tells us that f of x has to be of the form 1/3 x to the third minus 2x, or minus x squared plus c. So I want to be clear here. This is just telling us what the form of f is. This is not, and this is maybe deceptive to use this equal sign right here, this is not the actual solution. This is what any candidate for the solution must be like. Why is this? It's because we haven't specified that constant c right there. Once we specified the c, then we have a particular function. But until we specify it, what we have is a family of functions. And this equal sign is kind of deceptive for that reason. But all the same, it'd complicate things needlessly and introduce a lot of extra writing if we didn't write it this way. We're sort of abusing notation just for convenience. So we got to find out what that constant c is. We have determined that the solution is a member of a family of solutions, of potential solutions, of functions. All of these guys differ only by a constant, that constant c right here. Now, this is the general solution. This determines a family of curves shifted up or down, you know, a bunch of parallel translates of the same function, right? But it doesn't tell us which one should we choose. There's an infinite number of them, and we don't know which one we're supposed to select without this piece of data right here. We have to use this data. So let's use this. Okay, we're going to take our general solution. We're going to find out which c it should be using the initial condition f of 1 is 1/3. So we're going to find a particular function belonging to this family of functions using this piece of data, using this guy right here. We're going to use it. Okay, so we're going to solve for c just by figuring out what it has to be. If I know that f of 1 has to be 1/3, then I know, using the fact that my function f has to be like this, any possible solution has to be like this general form. They all have to be candidates, at least. They have to satisfy this thing right here. So we just plug in 1 to the general form. So f of 1 in the general form will be 1/3 times 1 to the third minus 1 squared plus c. Doing a tiny bit of manipulation, just looking at only the left-hand side right now, only over here, I'll see that I get 1/3 times 1 to the third, which is just 1, minus 1 squared, which is just 1, plus c. Okay, cool. Since I know that f of 1 has to be equal to 1/3, just using this guy over here, I'm going to replace f of 1 with 1/3. Hey, look, now at this point, I've got something that I can solve for c. I've got 1/3 equals 1/3 minus 1 plus c. So all I have to do is go, oh, okay, well, in that case, I could just subtract 1/3 from both sides and get that 0 is equal to minus 1 plus c. And doing a tiny bit of manipulation, just moving that minus 1 over to the other side, I get my answer. C is equal to 1. Is this the solution to the whole problem? No. This is the piece we need to get a solution to the whole problem. That is, we're going to take this guy right here, this candidate, this general form, and we're going to specify the particular solution using this extra piece of data. That is, we're going to replace this c with 1. So, doing that, we get f of x is 1/3 x to the third minus x squared plus 1, the constant that we found. And bam, this is the solution. Very cool. All right. So there are a lot of different types of differential equations out there. This is by no means exhaustive. We solved a very simple type of initial value problem right here, something of the form y prime is equal to g of x, and, y of 0 is equal to some value. Why not? We solve something like this. There are a lot more complicated differential equations. We could have something like y double prime plus 2y squared equals natural log of y triple prime times y minus 2. Who knows? We could have crazy stuff. Differential equations is a very large field, and there are a whole lot of different subfields. There are a lot of questions you could ask about a function given a differential equation. This right here, an initial value problem, is only one type of question you could ask. You could ask all sorts of other things. You could ask, what is the limit as, some value, maybe x goes to infinity, of the solution, y of x. You could ask, what does the long-term behavior of this function satisfy for any function that satisfies this equation? And you can do all sorts of crazy stuff. There's a whole lot of different things that you can ask about solutions to differential equations. You can even ask whether or not there are solutions to differential equations. There are even fundamental questions like that. And once you start introducing more derivatives, more than just first derivatives, once you start introducing multivariable functions, partial derivatives, and all sorts of stuff that we're not going to get into here, you can really quickly find that the field is incredibly rich. It's super fun. The study of differential equations is a varied and complex and undeniably rewarding field of mathematics to study. And this is your first little introduction to it. So, great, cool, something new.